Okay guys, what we're going to do today is basically a combination of the past 2 weeks or so. And we're going to be solving trig equations. Now you've already solved trig equations on several different occasions, but what we're going to do now is basically combine everything we've learned together to solve all the different types of trig equations you could possibly see. So the graphic organizer you guys picked up just has it separated into a couple different strategies, but similar to those proofs, every trig equation is going to be solved a little bit of a different way. And it's up to you guys to try to figure out how to best solve each equation. Now, I might run out of space here on mine because I need to write bigger for you guys to see, but if you want to make these fit in those boxes, you can. So the first strategy on there is taking square roots. Now, if you guys look, there's a big blank box there to start off with, because what you need to remember, anytime you take a square root, you need to include the positive and negative answer. So we're going to include both the positive and the negative. Now the question that we're going to solve that's going to use square roots is going to be 4 cosine squared theta is equal to 3. Now every question that you're going to be given when it comes to solving these equations is also going to give you a certain domain. And what that domain means is just where you want your answer to be. So one that we'll start with will say, it'll look something like this. It'll say theta or x, and you'll see a symbol there that looks a little bit like an E, but it's more curved. And this one's going to say real number degrees. And all that means, that's another way of saying find the general solution. That little E symbol, this is basically telling you that theta belongs to the set of all real number degrees. And all real number degrees is the general solution. So that's really just your code for general solution. So in order to solve these trig equations, we're going to follow a similar process here. What we're going to do is we're going to try and get the trig function by itself. So if I have 4 cosine squared theta is equal to 3, I need to get cosine by itself. So I'm going to start by dividing by 4. So I'm going to get that the cosine squared theta is equal to 3/4. Then to get cosine by itself, I'm going to take the square root. And this is when it's important for us to remember when we take a square root, I need to include the positive and the negative. So when I square root this, I'm going to get that cosine theta is equal to not only positive the square root of 3/4, but also the negative square root of 3/4. And remember, when you square root a fraction, you square root the top and you square root the bottom. So that should be a number that looks familiar to you guys. Root 3/2 is one of our exact values. And this one's actually a little bit easier if we find positive and negative, because we're just going to find every quadrant where this can happen. Because cosine is positive in quadrants 1 and 4, but it's negative in quadrants 2 and 3. And I need to find all of them, positive and negative. So let's just draw one of those. My adjacent is root 3, hypotenuse is 2, so missing side is 1. That means my reference angle is pi over 6. And I just need to find that pi over 6 reference angle in every quadrant. So in quadrant 1, that value is pi over 6. And actually I just realized we're supposed to be doing this in degrees, so I'll make this a little bit simpler. Instead of pi over 6, that's 30 degrees. So in quadrant 1, that's 30 degrees. And if I want to write the general solution in radians, it's plus 2 pi n, but in degrees, it's plus 360 n. Then I move into quadrant 2. I know the reference angle is still 30, but in quadrant 2, that value is 150. If I want the quadrant 3 value, it's going to be the reference angle plus 180, so that's 210. And then finally quadrant 4, that's going to be 330 degrees. If you want to, you could write that as negative 30, that's fine. That's still within all real number degrees, and it would still be the same answer. I just wrote 330 because we're going to be finding a lot of positive values coming up. So all 4 of these together make up the general solution to this equation. Okay, because we find where cosine is both positive and negative, root 3/2. So strategy number 1 is taking square roots. And again, the key there is to remember to include both the positive and the negative. Alright, so the next thing we may see is combining like terms, very similar to what we saw back in almost Algebra 1. So what we'll look at is, let's see if we have a question that's sine x minus 2 is equal to 5 sine x. So the key to this is just remembering sine x is a variable just like x or y or z, and we're going to treat it the same way. So in order to figure out what sine is, I'm going to get sine by itself on one side. And I need to include our domain here. This will be given to you in every question. Okay, this will be given to you on every question. So we'll look at one that's going to be very common for us. Let's say that x is going to belong to the set from 0 to 2 pi. And if you remember interval notation, 0 would be included in that set, 2 pi would not be included because of the parenthesis. So now to solve this question, I'm going to get sine by itself. So I'm going to subtract sine from both sides. So that's going to leave me with negative 2 over here, and then 5 sine minus sine. If I have 5 sines and I take away 1, I have 4 sines left. And then I'm just going to get the trig function by itself. So I'm going to divide by 4. And I get that sine of x is equal to negative 1/2. And then this is just a regular inverse question like we've been solving. We just need to keep in mind what our domain is. I want all the values between 0 and 2 pi. I like to start with the general solution. It makes it easier to make sure I'm including all of those values. So let's find both quadrants where sine is negative, and that's going to be in quadrants 3 and 4. So my reference angle in radians would be pi over 6. And in quadrant 3, that value would be pi plus pi over 6. So in quadrant 3, that would be 7 pi over 6. The general solution would be plus 2 pi n. Then in quadrant 4, I could make that value a negative 7 or negative 1 pi over 6, but to make this a little bit easier, I know my final answer needs to be between 0 and 2 pi. So let's go ahead and just write the positive value. It's 2 pi all the way around. The reference is pi over 6, so that means my answer here would be 11 pi over 6. Then if I was finding the general solution, it would be plus 2 pi n. Now in this case, I already have x by itself, so the general solution actually isn't going to change any of my values here. I don't need to use it to find any more of those values because the two I just found are already between 0 and 2 pi. And those are the only two values to my question that are between 0 and 2 pi. But it's not a bad choice to start with that general solution just to make sure in case you get something different. Alright, so the next thing we're going to look at, there's actually two different types of factoring that we're going to see. So the first kind of factoring is just taking out our greatest common factor. And if we're not sure where to go, it's usually the best first step. Greatest common factor is going to come up more often when we only have 2 terms, okay, instead of 3 terms. So let's look at something like this. Let's say my function is sine x times secant x, and I'm going to run out of space. So I'm going to have sine x times secant x, and I'm going to make that equal to sine of x. And my domain for this one, I'm going to make my domain a little bit different. I'm going to make my domain from negative pi to pi, just to make us think a little bit about this. Now the trick to solving this question, the fact that we're doing greatest common factor hopefully gives you a little bit of a clue here. What we are not allowed to do when it comes to solving trig equations, you cannot divide by a trig function. If you do, you will lose part of your answers. Okay, so you do not divide by a trig function, because we'll lose part of our solution. So what we're going to do instead is we're going to set this equal to 0 so that we can factor. If you guys remember solving by factoring in Algebra 2, the only way you were allowed to solve by factoring is if the equation was equal to 0. So my first step here is going to be to subtract sine x from both sides, and that's going to make my equation instead sine x times secant minus sine x is equal to 0. Once my equation is equal to 0, I can solve it by factoring. And in this case, like we said, this is greatest common factor. Both terms have a sine x that can get factored out. So sine x gets factored out, and I'm left with secant x, not by itself, but secant x minus 1. And if you guys remember, the way we solve by factoring is we take each factor and we set each factor equal to 0. and we solve both of those equations. So sine x is equal to 0. That means that x is going to equal sine inverse of 0. So I'm trying to figure out at what angle will sine be 0. And I'm going to go ahead and write my general solution here to help me figure out what's going to fit in my domain. So the answer to that part, sine is going to be 0 at 0 plus 2 pi n, and also at pi plus 2 pi n. Or if you wanted to write a really simple general solution, you could just say pi n. But right now we're just trying to find both places and seeing what that interval is. So those are the places where sine could be 0. I also need to solve the second half of my equation, and that's where secant x minus 1 is equal to 0. So I'm going to continue solving that up here where there's some more space. So secant x minus 1 equals 0. That means that secant is equal to 1. So I'm solving secant inverse of 1. So if you remember, secant is the reciprocal of cosine. So that's going to be the same thing as cosine inverse of 1 over 1, which in this case it makes it a little easy. It's still 1 for us. So I'm basically solving cosine inverse of 1 because the reciprocal of 1 is still 1. And cosine is 1, also at 0. So in this case it worked out that my answer was actually still included, but I need to make sure not to divide by that sign because I might have lost part of my solution. So the answer to this half of my general solution would be 0 plus 2 pi n. Now since that's already included, I can just look at this part of my solution, and I'm trying to find all of the values between negative pi and pi. And they're in brackets, which means that it's included. So I look at my first part of my general solution. 0 is included in that answer. So 0 is part of my answer. If I add pi to 0, or if I add 2 pi to 0, or I subtract 2 pi to 0, it's no longer in that range. So there's nothing else I can get from that part of the general solution. Pi is within that range. If I add 2 pi and get 3 pi, that's outside of it. But if I subtract 2 pi, I get negative pi, which is also included in my range. So all 3 of those values are within my domain. All right, so the last kind of factoring that we're going to look at is quadratic factoring, which is 3-term factoring. Now, you did a lot of this in Algebra 2, and I know some of you guys might need a refresher. This is going to be really important for us, and it's going to come up quite a bit. So this would be something like 2 sine squared, and I'm going to run out of space again, 2 sine squared x minus 5 sine x is equal to 3. Now I don't want to solve this with a greatest common factor because it's not equal to 0. So you can only solve by taking out a greatest common factor when it's equal to 0. So do not solve by factoring if it's not equal to 0. So we're going to make it equal to 0. I'm going to subtract 3. So I've got 2 sine squared minus 5 sine minus 3 equals 0. And now I need to factor this equation. So if you remember, sine x is a variable. We treat it just like regular x. And this is going to factor just like 2x squared minus 5x minus 3. And you factor things like this all the time in Algebra 2 and actually even in Algebra 1. We're going to do a quick little review here, except everywhere there's an x, it's actually sine of x. So I'm going to do my a times my c, and that's negative 6. So I need 2 numbers that multiply to negative 6 that add up to a negative 5. And those numbers are going to be a negative 6 and 1. So I split up the middle with the 2 terms I just said. So I have 2 sine squared x, and then instead of minus 5, I now have minus 6 sine x plus sine x, because the 2 numbers I came up with were minus 6 and 1. I still have minus 3. And then I factor by grouping. So I look at these first 2 terms and I see what's common. So 2 sine comes out. I'm left with sine x minus 3. Then I look at my next 2 terms and I see what's common. There's nothing common, so it's just going to be a 1. I keep the plus, and then if the 1 comes out, nothing changes. It's sine x minus 3. And we know we factored it correctly if these 2 sets of parentheses match. So the set of parentheses that matches, that's my first factor. And everything that's left over, that's my second factor. So now in order to solve this, this whole equation is now equal to 0. Just like I did with greatest common factor, I take each factor, I set it equal to 0, and I solve each part separately. So the first part I'm solving here, sine x minus 3 equals 0. If I get sine by itself, I'm looking for where sine of x is equal to 3. And if you guys think about that, that means an opposite of 3 and a hypotenuse of 1, which we know can't happen. So this factor actually doesn't lead to any solutions for our equation, so we don't have to go any further with that. So the only solutions I'm going to find are for this factor over here. So I know that 2 sine x plus 1 is equal to 0, and I'm going to rewrite this at the top where there's some more space. And all I need to do, just like the very first question, is get sine by itself. So subtract 1 divided by 2, I get that sine x is a negative 1/2, so I'm solving sine inverse of negative 1/2. So I'm looking for the two quadrants where sine is negative. So sine is negative in quadrants 3 and 4. And this should look familiar because we already did something very similar in our previous question. Reference angle here is 30 degrees. Oh, and I didn't give you guys your domain restriction here. Let's find our answers between, let's say that x is from 0 to 2 pi. So I'm looking for the radian values, and I want the positive values to make this a little bit easier. The reference is pi over 6. So in quadrant 2, it's pi plus pi over 6, which is 7 pi over 6. And in quadrant 4, negative pi over 6 would be the same thing, but again, since I want my answer between 0 and 2 pi, let's go ahead and find the positive value, which would be 11 pi over 6. All right, now there's just one last strategy to look at, and we've actually done a couple of these, so we're not going to do a full example here. I just want to show you guys how to kind of set up your first step here. So this is using our trig identities. So our trig identities will help us if we have kind of a complicated question and we can't see how else to work it out. Again, we're just going to show the first step here. Let's say I have a pretty complicated equation that looks like this. So if I look at that, and that's a negative root 3 over 2. It's kind of hard to see, sorry. If you guys look at this at first glance, it's going to be really difficult to solve. I can't actually factor anything out because the arguments are different. You guys might think you want to use some of your double angle properties, and it's going to make it really messy. But if you look really closely at this, this actually looks like one of your sum and difference properties. Because I have sine times cosine minus cosine times sine. And your A is actually the 2x, and the B is actually the x. So if you guys recognize that, sine times cosine minus cosine times sine is my sine A minus B. But my A is 2x, my B is 1x. So I actually could solve this question just by using that property. By simplifying it with that property, I now have that sine of x equals negative root 3 over 2. And it's just a regular basic inverse question. Alright, so that's just a couple of the different strategies you guys are going to see when it comes to solving these trig equations. Each one's going to be a little bit different, but these are some of the most common strategies. And we're going to do a lot of this over the next 3 days.